My dear student, today let us talk about some more example, very important example of linearization. So here we are going to consider two systems. We are going to find two systems, two non-linear system whose linearized systems are equal and whose linearized system has center as a fixed point, or every center is a stable fixed point, and the linearized system has, you know, center as a fixed point, but there are non-linear parts. One is spiraling inward, another one is spiraling out. That means when the case of spiraling in, that is strongly stable. When the case is spiraling out, that is strongly unstable. So that is the case. Linearization theorem says that if the linearized system has center as a fixed point, then there are two possibilities. Number one possibility is that the non-linear system has stable center, and the non-linear system, another possibility is that the non-linear system has, spiral fixed point. So in case of spiral fixed point also, there are two possibilities. One is spiraling inward, that is strongly stable, and another one is spiraling out, that is strongly unstable. So that is the case. So let us discuss this example. So that for each of the following nonlinear system, the origin is a center for each of the linearized system. That means for this nonlinear system, the origin is a center, that is stable center for the linearized system, and for this nonlinear system also, the origin is the center, that is stable for the linearized system. Okay, but their linearized counterpart has same behavior. They have same behavior. The fixed point have same behavior, but the non-linear system, they have different behavior. So that is the that is the one I want to tell you, especially for the case of center. In other cases, no, if the linearized system is stable, the non-linear system is also stable. If the linearized system is unstable, the non-linear system is also unstable. So but in the case of center stability, or in the case of center is always stable fixed point for linearized system, but for the non-linear system, many things can happen. Okay, that is, this is the example to support that one. Okay, so let us see. To find out the fixed point is not that difficult. You can do that one. The first system also has 0 0 as a fixed point. Okay, this 0 0 fixed point for the first system. For the second system also, this is the fixed point. So you can do that one. How to find out the fixed point is not new to you. So for the first system, 0 0 is a fixed point. For the second system is also 0 0. The origin is a fixed point. So now, let us, the linearized system for this, the first system, the linearized system is this one, and for the second system also, the linearized system is this one. So that's how to linearize it. In the previous class we discussed how to linearize it. Now I will tell you a shortcut method. So the given system is what, dx1 by dt, this is equal to, so how much, let us see, look back, it is equal to x2, it is equal to x2 minus x1, no, it is equal to x2 minus, it is equal to x2 minus x1, then x1 square plus x2 square. This is the first equation of the first system. And let us see what is the second equation of the first system. Minus x1 minus x2, that is what, dx2 by dt, dx2 by dt, this is equal to minus x1 minus x2, x1 square plus x2 square. So this is 0 0 is a fixed point, and 0 0 is a fixed point. So we want to linearize it about the fixed point 0 0. So what to do, it is very easy. You just neglect the non-linear term. This is the non-linear term because it will give you x1 cube minus x1 x2 cube, and this one also it will give you x2 x1 square minus x2 cube. So non-linear term will arises from here. You just eliminate this one, then what is the equation? The x1 by dt, this is equal to x2, and next equation is the x2 by dt, this is equal to minus x1. So this is the linearized system about the fixed point 0 0. So if the fixed point is 0 0, the origin for the nonlinear system, then the linearized system will give you, the linearized system is very easy. Just neglect all the nonlinear terms, just neglect all the nonlinear terms, then you will get the linearized system like this. Okay, so that is the easier method, that is easy one, and otherwise you can find out the partial derivative at a fixed point and do that one. You already knew that one, I explained you in the previous class. So using that method you will get, this is the linearized system of the first system of nonlinear equation about the fixed point 0 0, and this is the linearized system of the second system of nonlinear system about the fixed point 0 0, that is the origin. So you can see they have same linearized system, x2 minus x1 minus x1. So the two nonlinear system has same, they have same linearized system. So what is the matrix form then? The matrix form is given by the x by dt is equal to x, where a is equal to 0 1 minus 1 0. So what is the root of this, what is the eigenvalue of this matrix? You can find it easily. So this matrix, your matrix A is equal to 0 1 minus 1 0. So you can find it easily that the eigenvalues or the characteristics roots are given by plus minus I. This is the, so if the eigenvalues are purely imaginary, then the solution curves x1 and x2, they are circles. So then the phase curve eliminating time relation between x1 and x2 will be a circle. So therefore the fixed point is a center, and that is stable. So the linearized system has, the linearized system has origin as a stable center for both the system 1 and system 2. That is quite obvious from here. All right. So and then analytically also you can do that one, you can solve it. We can solve this equation by eliminating time variable and solving by separation of variable like this. So you see dx2 by dx1 is equal to minus x1 by x2. So by separation of variable you will get x1 square plus x2 square. This is the phase curve. Okay, so the phase curve is like this, therefore the center is a fixed point. Okay, so you can draw the phase curve also like this. So what does it say? What does it say is that, suppose this is your x1 variable and this is your x2 variable, this is x1 variable and this is x2 variable, and 0 0, this is the fixed point. The phase curve will be like this circle. The phase curve is like this. So this is the fixed point. The phase curve is like this. The phase curve point on the phase curve is neither moving in toward the fixed point nor moving away from the fixed point. So it is stable. It is there. Okay, so if you start from here it will be like this. Okay, if you start from here it will be like this. So the phase curve, okay, but the phase curve is a concentric circles. Okay, system of concentric circles. So it is stable. It is called center because it is in the center of the circle. Okay, so it is stable center. For the linearized system it is stable center. Okay, so this represent, this represents circles. So the linearized system has center as its fixed point and center is always stable. So For the linearization theorem, what do we see? For the studying the stability of the fixed point of the nonlinear system, we linearize it and look at the nature of the fixed point of the linearized system. So here we are having center as a fixed point of the linearized system. So there are two possibilities for the nonlinear system. One is center, that is stable. Another one is spiral. So in case of spiral also there are two possibilities. One is spiraling inward, that means strongly stable. Another one is spiraling outward, that is strongly unstable. Okay, so these are the possibilities when the linearized system has center as a fixed point. Okay, so now let us see the behavior of the fixed point for the non-linear system. For the linear system it is stable center. Okay, and for the non-linear system, let us see. So use coordinate, using the polar coordinate, what do you get? Polar coordinate x1 is equal to r cos theta, x2 is equal to r sin theta. And now let us differentiate x1 with respect to time variable. You will get this one, cos theta dr by dt minus r sin theta d theta by dt, and dx2 by dt is equal to r this one, sin theta dr by dt plus r cos theta d theta by dt. Okay, so then let us substitute this value in the equation, first system of equation. Okay, on substituting in the first equation of 1, we get what? You get this one, equation A you get. And from second equation of the system, first system, from the second equation to the first system, you will get this one. Okay, equation B. So now let us multiply equation A by cos theta and equation B by sin theta, and let us add together. What do you get? So this is cos square theta, this is sin square theta, common, dr by d theta is common. So cos square theta plus sin square theta is 1. So you will get on the left hand side dr by d theta. Okay, and this term will cancel out with this term after adding, and this one also will cancel out. So what do you get? So r cube cos square theta plus sin square theta is there, minus r cube. So then ultimately in the simplified form you get dr by dt is equal to minus r cube. Again, now let us multiply equation A by sin theta and equation B by cos theta, and let us subtract. Okay, and then subtract. After subtraction you will get what? D theta by dt is equal to minus 1. So using polar coordinate system, the given system of nonlinear system of equation, system 1, is reduced in this simple form. Okay, in this simple form. All right, so what does it say? Is d theta by dt is minus 1. It is negative. No? That means when theta is decreasing, r is also decreasing. Okay, when theta is decreasing, r is also decreasing, because dr by dt is always negative, because r is radius vector is supposed to be positive. So here also d theta by dt means theta is decreasing, it is negative. No, so it is decreasing. So when the theta is decreasing, r is also decreasing. So but this one, what is similarly from the system, from the second system of equation, after using polar coordinate, you will get this system. But this one, when theta is decreasing, r is increasing. All right, so from now we have first system correspond to this system C, and second system correspond to this system D. From C you can solve it easily by eliminating the variable t, or you can divide first equation by second equation, and then you will get separation of variable. You will get dr by d theta is equal to r cube. So after solving you will get this one, r is equal to 1 upon root over c minus twice theta, where c is a constant. All right, so like that. So what the first one, let us see the first one, what does it say? Let us see diagram. This is the case of linears. This is the case of both the system has same linear system, and nature is also same in the stable center. For the non-linear system, the first one, what does it say? The first one, let us see. The first one says that what? Say first one dr by d theta dt, dr by dt is equal to, this is equal to minus r cube, all right, and d theta by dt is equal to minus 1. So d theta by dt is always negative, means when theta is decreasing. Yes, this is the one. So what does it say analytically? What does it say? That means d theta by dt is negative, means theta is decreasing as time increases. So suppose this is the let us see the phase curve nature radius vector. So this is the first radius vector r. When theta decreases, r is also decreases. Then theta decrease means in this clockwise direction, it is coming to clockwise direction. When theta is decreases, r is decreasing like this. Okay, so it will be like this, spiraling in. Okay, spiraling in. When theta decreases, r is decreasing. All right, so that is the case. So this is the strongly stable case. When theta decreases, r is also decreases. All right, so this is the case of strongly stable, spiral, strongly stable case. So the first non-linear system is a strongly stable, okay, fixed point. All right, because as time tends to infinity, radius vector is tending toward 0, toward the origin. Okay, so it is the case of strongly stable case. Let us see for the second one. Let us see for the second case. What does it say? Yeah, similarly from the second, similarly from the system D, we get this one. So what does it say? When this says that when theta decreases, r is positive, r is always positive, radius vector distance is always supposed to be positive, r cube. So when d theta by dt is negative, means when theta decreases, r is increasing. So how does it look like? Let us translate it into the phase curve. Let us translate. Let us try to draw here more nicely comparison to the earlier one. So here the system is what? Dr by dt, this is also this is positive r cube, and d theta by dt is negative minus 1. That means when t increases, theta is decreasing. So when theta decreases, but r is always positive, so r is increasing. So when theta is here, when theta, this much is your theta. All right, this much angle. Theta in decreases means what? From earlier it is here theta 1, now it is theta 2. It is decreasing, no? So when theta decreases, what happened? When theta decreases, what happened? R is increasing. So R will be increasing, means this much is R, then it is increasing like this. So it will be like this. What? It will be spiraling out like this. Okay, all right, so this is the case of spiraling out. That means what? It is moving away from the fixed point, it is unstable. But in this case, when theta decreases, r is also decreased. That means it is coming toward the fixed point. So what is the conclusion from this example? We have two nonlinear system. Okay, both the nonlinear system have same linearized system. Okay, therefore their linearized counterpart have same stability nature, that is center. Okay, but their counterpart, nonlinear counterpart, they have very, very diverse behavior. One is spiraling inward, that is strongly stable. Another one is spiraling outward, this is strongly unstable. Okay, so that is the case we have now. And this is very important example. It can be asked in examination by giving you 10 marks also. Similar example also I can ask. So let us see. In this case, the phase portrait is a spiral one. Okay, phase curve or phase portrait is a spiral. Okay, spiral. For system 1, since dr by d theta is negative for all r greater than 0, the phase curve spiral inward leading to a strongly stable fixed point at the origin. On the other hand, for the system 2, dr by d theta, dr by dt is positive for all r greater than 0. The phase curve spiral outwards, leading to a strongly unstable fixed point at the origin. Okay, so this is the case. So yeah, this much I want to give you today. This is very important. Similar example I will upload you in WhatsApp, screenshot of some example I will upload in WhatsApp. You solve it, and you again after solving take a screenshot and send to me. I'll check that one. All right, so this much I want to give you today. All right.